In the dynamic study, these are the four fundamental equations that we use for a particle. For the first equation, you have the velocity equal to dx over dt, where your x is the displacement and your t is the time. Velocity is the change of displacement over time. If a particle moving to another position over time, then it will experience the velocity. For the second equation, you have the acceleration a, which is equal to the change of velocity over time. In this case, the particle is moving from point 1 to point 2, and the velocity remains the same 10 meters per second. In this case, the velocity is constant, therefore your change of the velocity will be equal to 0, and the acceleration will be equal to 0 as well, for a constant velocity. If the velocity increases from 10 to 100, then you will obtain positive acceleration. If you have a negative acceleration, you need to be careful that this does not mean that the particle moves backward. So this is wrong. Negative acceleration means that the velocity is decreasing with respect to time. If you have positive velocity, like this case, it means that the particle will move with respect to the positive axis. For example, positive x direction here. If the velocity is 0, it means that the particle 3 here is not moving, which is in rest position. If the velocity is in negative, for example, the velocity at particle 4 here is -5, it means that it's moving in the opposite direction to your axis. So you should expect the particle 4 move in the negative x direction. So this is our equation 1 and 2, and they are called the first and second kinematic equations. From the Newton's second law, we have the first kinetic equation. We can use this equation to find out what is the force that is required to move a mass moving with an acceleration a. In the last equation, you have x equal to r theta, and the x is the displacement that you experience during the linear motion. For example, you are moving from one point to another point in linear motion. We can use this equation to convert the linear motion x to the angular motion theta. Theta is the angular displacement. The unit is radian. If you want to convert to degree, you have to multiply with 180 divided by pi. Then you can convert the unit of theta to degree by using this formula. From these two equations, let's rearrange the dt on your left hand side. Then you obtain dt equal to dx over v and dt equal to dv over a. If you multiply v, then this term will cancel. You have v dv here. Multiply a, then this term will be cancelled and you have the a dx. So you success to obtain the third kinematic equations from the previous two fundamental equations here. Let's divide both sides with dx, and you should be able to obtain the a equal to v dv divided by dx. Once you substitute the third kinematic equation into the kinetic equation here, then you should be able to obtain this. Your f is equal to mv dv over dx. Let's multiply both sides with dx. Then this will cancel and you have f dx. On your left hand side, the limit for the dx is x1 to x2, and the limit for dv is v1 to v2. When you integrate v with respect to v, then you should have mv squared over 2. Once you consider the lower and upper limit, then we can substitute to obtain this answer. So you substitute the v2 inside v here, you obtain mv2 squared divided by 2, and then you substitute v1 inside, you have the negative 1 over 2 mv1 squared. With that, we success to obtain the second kinetic equation using the principle of work and energy. If you substitute equation 2 into the a here in the equation 3, then you obtain f equal to m dv over dt. Let's multiply both sides with dt. Then this part will be cancelled. You have dt multiply f here, So we can continue to integrate both sides. So you have the t here, therefore your limit is changing from t1 to t2. And over here you have the limit v1 to v2. Then you should obtain this equation, and we integrate 1 inside here. So for constant 1, if you integrate, you obtain v. Don't forget the constant m. So if you consider the limit as well, v1 to v2, then we have to substitute v2 inside, you obtain mv2, minus with v1 inside, you have mv1. This equation is known as the third kinetic equation, using the principle of linear impulse and momentum. In this case, we have a rotor here, where you can imagine the rotor is rotate in the counterclockwise. If the rotor is rotate with 30 degrees and the radius of the rotor is given by 1 meter, what will happen to this object? What is happening here is actually we are converting the angular motion of the rotor to the linear motion. The linear motion of this object can be predicted by this equation, where you have x equal to half theta. You need to be careful that the theta must be in radian, therefore you have to convert 30 degrees to radian by using this formula. From the result, you can see that if you rotate the thing by 30 degrees, the object here will move in linear motion by 0.5. The distance from the original position to this position is the same with the distance from the original position here to this position. If we substitute the angular equation 4 into equation 1 here, so you have the dx over dt become dr angle divided by dt. So since r is constant, we can take it out, and inside the component you have the angle divided by dt. Since we know the omega, which is the angular velocity, is the change of d theta, which is the angular displacement, with respect to time, we can substitute the omega equal to d theta divided by dt here. We can further substitute the v equal to r omega inside the second equation here. Then we can have a equal to r d omega divided by dt. The alpha is the angular acceleration, which is equal to the change of angular velocity d omega divided by dt. Then we can substitute alpha to be this answer. From these two equations, we can obtain the first and second angular kinematic equations, where you have the angular velocity equal to v divided by the radius, and the alpha equal to the acceleration divided by radius. If we cancel the radius both sides, then we take out the dt, then you should obtain the dt equal to d theta divided by angular velocity equal to d omega divided by angular acceleration. Rearrange this equation, then you should be able to obtain alpha d theta equal to angular velocity omega d omega. So this is the third angular kinematic equation. In summary, this is the useful kinematic equation for a particle, in terms of linear motion and in terms of angular motion. In the linear motion, what we are interested is about the displacement, velocity and acceleration. On the other hand, for the angular motion, what we are interested is about the angular displacement, angular velocity and angular acceleration. You see that we can convert the linear motion x, v and acceleration to the angular motion by multiplying it with r, which is the radius. Without derivation, we can find the kinematic equation for the angular motion by linking the linear motion equation. For example, let's say we have v dv equal to a dx, and in linear motion, the velocity is changed to omega in angular motion. So we can just replace the v to be omega here. And then the acceleration will be alpha. So you change the acceleration to be alpha, and your displacement x to be theta, which is the angular displacement. So with that, without doing the derivation, we can obtain a new equation for angular motion purpose. By using the same approach, we can change this equation into angular type, where you have the acceleration changed to the angular acceleration alpha, velocity changed to angular velocity omega. So for this equation, we are doing the same thing, where your velocity can change to angular velocity by replacing the v to be omega, x to be theta. By using the same approach, let's look at the kinetic equation. For linear motion, we have the force causing a mass to move in acceleration. So for a angular motion, you have the moment m cause the moment of inertia I to move with angular acceleration. So you see that in linear motion we have force, in angular motion we have the moment that cause rotation, and for a mass m, linear motion we have m, so m is the inertia in a linear motion, and you have I in the angular motion. So in this equation we have the work done and the energy change, and you can see we can convert this to the angular type by replacing the x to be the theta, the force to be the moment. This is called the principle of work of moment. The kinetic energy due to the linear motion can be converted to the kinetic energy due to angular motion by change the m to capital I, velocity to omega. Lastly, you have a linear impulse that can be changed to angular impulse by change the force to moment. This is the change of linear momentum, and we can change it to the angular type here by replacing the mass m to the I, and then velocity to the angular velocity omega. So these are the useful formula for the kinematic equation as well as the kinetic equation that you must know. As I showed you earlier, as long as you know the equation for the linear motion, then you can convert to the angular type easily. So you do not need to memorize this formula.